Welcome to Maths with EJD. We've been talking about numerical analysis and we've done a lot of things. Right now, we are switching gear and we are talking about the numerical solutions of initial and boundary value problems for ordinary differential equations. Okay. And the objective is to gain a foundational understanding of ordinary differential equations. ODEs are ordinary differential equations, particularly initial and boundary value problems, and learn various techniques for solving them. So let's look at key concepts in this regard. Key concepts here. Key concepts. So first of all, we talk about initial value problem. Initial value problems. IVPs. I'm here to do a playlist on actually on differential equations generally, but definitely it's going to come. But then the numerical thing is coming first, so that's fine. So initial value problems. So what does this mean? An initial value problem consists of a differential equation. It's a differential equation along so you have a differential equation along with an initial condition. You have an initial condition, more like a starting point, right? An initial condition. The general form, the general form of a first order initial value problem, IVP, is this. You have dy dx equals f of x comma y equals f of x comma y, and then you have the initial condition attached. Y of x, y x naught equals y naught. So this is what a first order because the derivative is of order one. If you have d squared y dx squared, that'll be order two, right? So an IVP has these two parts. You have the differential equation, whether it's ordinary or not. In this case, we have an ordinary differential equation, and then you have this whole thing as the initial condition. Okay, this is the equation, the ODE, and this is the initial condition. So it means you have a starting point for the equation, right? Now, the goal in this situation, the goal is to determine, the goal is to determine the function y of x that satisfies the equation, that satisfies the equation, that satisfies this equation, this equation, while also fulfilling, while also fulfilling the given initial condition, the given initial condition. So IVPs, initial value problems, are commonly solved. They are commonly solved using methods such as, okay, I like to list these ones. So such as separation of variables. When I finally get around to doing talking about differential equations, not numerical now. I'll be dealing with all of this. Separation of variables, integrating factors, integrating integrating factors, and so on and so forth. So you can use this kind of methods, or you can also have the numerical approach, like the Euler's method. There are so many methods, but we'll be focusing on two in this playlist: Euler's method, Euler's method, or what you can call the Runge-Kutta methods. Runge-Kutta methods. So, I mean, we've lumped everything together, but you should understand that these first two methods are analytical methods, the analytical solution methods. Whereas here we are more concerned with numerical solution methods. So Euler's method and Runge-Kutta methods are actually numerical methods, and those will be our focus in this playlist, numerical methods. So so for initial value problems, two of the most popular, two of the most popular method, numerical methods are Euler and Runge-Kutta methods. So, I mean, you have every other methods like that, but we'll be focusing on this in this situation. So that's talking about initial value problems, where you have a starting point, an initial condition, you have a differential equation and an initial condition attached to it. Okay, let's talk about boundary value problems. We're still talking about key concepts under numerical solutions of initial and boundary value problems for ordinary differential equations. So we've talked about initial value problems. Now let's talk about boundary. So initial, you have a starting point. What about boundary? Boundary, you have points at two edges, at two ends. So you have boundary value problems. Boundary value problems. We call them BVPs, boundary value problems. Unlike IVPs, that's initial value problems, boundary value problems, that's BVPs, specify conditions. They specify conditions at more than 1 point. So a general, okay, I guess I want to color code at this point. A general boundary value problem can be written as this. You have d squared y, dx squared equals g of x of y, g of x of y, and of y prime. Okay, maybe you're told to solve this. Solve d squared y dx squared equals g of x of y and y prime, subject to boundary conditions such as y at the point A is equal to alpha and y at point B is equal to beta. So a very good case in point for this would be in heat or wave equation, right? For heat equation, if you have a metal bar, for instance, you have boundary conditions, right? Maybe the heat at you have a bar of a particular length. Say, let's say this is a particular bar now. So maybe there's a particular heat temperature at this point, and there's another one here. So these are like boundary conditions in that situation. So, or you can also have wave equation, like maybe in a guitar string, you want to see the wave getting happening in that place. So you can have boundary condition in that kind of situation. Okay. So what are we doing here? What is our goal in this situation? Here, the solution must satisfy conditions, at both boundaries, so to speak, at both x equals a, that's the a you see here, x equals a, and X equals B, like here. Those are the boundaries. So these problems often arise, often arise in physical systems, in physical systems like heat conduction, like I said before, heat conduction, wave motion, like wave motion in a string, wave motion, and structural analysis, like in civil engineering, structural analysis. So when you talk about frames and trusses and all that, structural analysis, and they require they require numerical methods basically. So it's difficult to find an analytical solution for this kind of problems. And they require numerical methods like, we are going to consider this too. You have finite differences. So the first time we mentioned finite differences was under numerical differentiation. So finite differences are really useful in this situation too. And we also have what we call the um, shooting methods. So you have finite differences method, and then you also have shooting method. They are numerical in nature, and we are going to consider the two of them in this playlist. So and they require numerical solutions like finite differences method and shooting method for solutions, for solutions, because analytical solutions are hard to come by. They are hard to come by. Okay. Analytical solutions are almost impossible, if not impossible altogether. So let's take an example. Well, I may not release, but I'll just make reference to it. Basically, imagine this example. Consider the first order differential differential equation, dy dx equals x plus y, then y of 0 equals 1. This is an initial value problem, actually. So over the interval, x belonging to the closed interval 0, 1. Okay. So this problem, for instance, it has an analytical solution. So let's look at this. So first of all, let's consider an analytical solution. I won't solve it. I'll just make some comments. So we have analytical solution to this. Like we said, right, for initial value problem, you can find analytical solutions like separation of variables or integrating factors method. So this one fits into one of those categories. So for analytical solution, right, you need to use integrating factor. So I'll just mention that and give you the results. So for analytical solution, linear, this is a linear first order. It's a linear first order equation and can be solved using the integrating factor method. So watch out for my playlist on differential equations. I'll be talking about all this, but here we are focused on the numerical part using the integration factor method. Okay, so that can happen, right? So if you go through all the process and use the integrating factor, you end up getting the results. So the final solution is y of x equals 2e raised to power minus x plus x minus 1. So that is the final solution for the final analytical solution. I mean, the process, I can go through the process, but yeah, that's not my focus in this place. Now, you discover when you solve a function, you get a variable. Like when you solve y of, for instance, now this is a function. If you equate it to zero, you can solve for x using any of the methods you have used, like Newton-Raphson or bisection or anything like that. So that's fine. But when you solve a differential equation, you get a function. So you can see how it goes. Solve a differential equation, you get a function. Solve a function, you get a variable, you know. So what that's why when you solve a differential equation, you're expecting to get y of x or x of t or whatever it is your focus is about. So that's the analytical solution for this particular problem now. So, but our focus, like I said, is the numerical side of things. So I'll go for that also. Imagine you now need the numerical solution for this numerical solution. So just like I said, there are two numerical solutions I've outlined. There are so many, but you can use Euler, you can use Ronchi-Coulter. So if and so up there we already got a numerical solution, right? But in case an analytical solution, in case an analytical solution is not feasible, is not feasible, numerical techniques, numerical techniques such as Euler's method, Euler's method, or Runge-Kutta or Runge-Kutta methods can be applied. Can be applied. Okay. So for instance, for Euler's method, we approximate y of x iteratively using yn plus 1 equals yn plus hf of xn yn. Okay, so that's the Euler's method. So here, where h is the step size, I've been talking about step size a lot. So given the initial condition y of 0 equals 1, so we compute successive, so it's numerical solution now, right? So we compute successive values for x, which is 0 0.0, 0 0.1, 0 0.2, and you keep at that until you get to 1.0. So that's that's the Euler thing. So Euler method, that's the most basic. But then sometimes may be interested in higher accuracy. So for higher accuracy, Runge-Kutta methods, particularly the fourth order, Runge-Kutta, RK4 for short, are often used. Okay, so that's how that goes. So this is just an introduction to all that. So in the next video, I'll be looking at the Euler method in some detail to show us how that goes. Then I'll be showing you the Python implementation. After that, I will go ahead and talk about the Runge-Kutta fourth order method. Then we'll move on to boundary value problems, where we'll talk about finite difference method, as well, and later we'll talk about shooting method, and we keep moving like that. So there's a lot to learn right here. If you have subscribed, thank you for that. If you have not, you don't want to miss out on anything again on this channel. So be sure to subscribe to the channel and hit the notification bell so you can always get alerted each time a new video is released. Then comment, let me know how helpful these videos are. Let me know if there's a topic you'd like me to teach or a problem you'd like me to solve. And finally, like and share so that more people can have access to this great content, because it's quite helpful. Till then, Till I see you again, keep doing maths right. Bye.